Mars isn't dead. Scientists drilled deep, found organics, and now the entire scientific community is freaking out. What they discovered suggests Mars once had everything life needs. This is the proof that everything we thought about our dead neighbor was completely wrong. And here is a question. If you were the first human to set foot on Mars, what's the very first thing you'd do? Let me know in the comments. I will pin the most creative answer. Now let's begin. 3.5 billion years ago, Mars was a world transformed. Liquid water flowed freely across its surface, carving channels through rock, filling enormous craters that became lakes, perhaps even forming vast oceans in the northern lowlands. The atmosphere was thicker, warmer, more protective, conditions that, according to everything we understand about biology, could have supported life. Think about Earth during that same period. Our planet was teeming with microbial life. Simple organisms were thriving in oceans, in hot springs, beneath rocks, everywhere water touched mineral surfaces. If Mars had similar conditions, why wouldn't life have emerged there too? This question has haunted scientists for generations. And now we might finally be approaching an answer. The story begins in a place called Jezero Crater, a 45-kilometer-wide impact basin on Mars that once held a deep lake. NASA chose this location specifically for the Perseverance rover because billions of years ago, rivers flowed into this crater, depositing sediments rich with organic material. If life ever existed on Mars, this would be the perfect place to find evidence of it. Perseverance landed in February 2021 with a mission unlike any before it. This wasn't just about exploring. This was about collecting samples that would eventually return to Earth, samples that could definitively answer whether Mars ever hosted life. Equipped with sophisticated instruments capable of analyzing rock composition at microscopic scales, the rover began its methodical search through the ancient lake bed. In September 2025, something remarkable happened. Scientists announced the discovery of a rock formation they named Bright Angel, located in an ancient river valley called Neretva Vallis on the western edge of Jezero Crater. This wasn't just another Martian rock. Inside it, researchers found something that made geologist Michael Tice, a research scientist at Texas A&M University, unable to sleep. The rock contained sub-millimeter scale nodules and millimeter scale reaction fronts. Fancy scientific terms, but here's what matters. These features were enriched with ferrous iron phosphate minerals, likely vivianite, and iron sulfide minerals, probably greigite. Even more intriguing, organic carbon-bearing compounds were found intimately associated with these minerals. This combination, this specific arrangement of chemistry and structure, tells a story. Make sure to give this video a like. Your support genuinely helps this channel grow and allows me to bring you more content. It makes a huge difference. Now let's talk about what makes the Bright Angel discovery so extraordinary. The minerals found in this formation, vivianite and greigite, form through specific chemical processes called redox reactions. Redox is short for reduction oxidation, processes where electrons transfer between molecules, changing their chemical states. On Earth, these same minerals often form in environments where organic matter decays, where life once existed. Here's where things get truly compelling. The arrangement of these minerals wasn't random. They formed in nodules and reaction fronts, structures that suggest chemical gradients existed in the ancient Martian environment. Imagine an underground layer where water seeped through sediment, carrying dissolved minerals. Where that water encountered organic matter, chemical reactions occurred, precipitating the iron phosphate and iron sulfide minerals we see today preserved in the rock. The geological context matters enormously here. Scientists determined these reactions occurred at low temperatures, not in some volcanic hellscape, but in relatively gentle conditions compatible with microbial life. On Earth, when we find similar mineral assemblages in similar contexts, biological processes are frequently involved. Not always, but frequently enough that we cannot ignore the possibility on Mars. Nicola Fox, Associate Administrator for Science at NASA, didn't mince words during the press conference. She stated this represents the closest scientists have actually come to discovering ancient life on Mars. Not definitive proof, not yet, but the closest we've ever been. That statement carries enormous weight coming from NASA's top science official. It reflects years of careful analysis, peer review, and scientific scrutiny. The findings were published in the journal Nature on September 10, 2025, one of the most prestigious scientific publications in the world. Getting research published in Nature requires extraordinary evidence and rigorous methodology. The fact that this study passed that threshold tells you how seriously the scientific community takes these results. But perseverance isn't working alone in this cosmic detective story. Its older sibling, the Curiosity rover, has been exploring a different region of Mars since August 2012. Curiosity landed in Jezero Crater, another ancient lakebed, and has spent over a decade analyzing rocks, drilling samples, and sniffing the Martian atmosphere for clues about the planet's past. In 2020, Curiosity conducted an experiment that had never been attempted on another world. The rover drilled into a rock sample nicknamed Mary Anning III, named after a famous English fossil collector and paleontologist from the 19th century. This sample came from a clay-enriched region where lakes and streams existed billions of years ago, a landscape formed when water was abundant and Mars was potentially habitable. Curiosity carried something special in its arsenal: 2 sealed cups containing a chemical reagent called tetramethylammonium hydroxide, or TMAH for short. This chemical can break apart organic molecules, revealing their underlying structure and composition. Scientists call this process thermochemolysis. It had been performed thousands of times in laboratories on Earth, but never, ever on another planet. Amy Williams, an astrobiologist at the University of Florida and leader of the Curiosity science team, described the pressure they faced. They had exactly 2 shots to get the experiment right. 2 cups of reagent, 2 chances, fail, and years of planning would be wasted. The stakes couldn't have been higher. So they chose their target carefully, drilled precisely, and executed the procedure flawlessly. The results, published in Nature Communications in April 2026, exceeded even their most optimistic expectations. The experiment detected more than 21 different carbon-containing organic molecules in the Mary Anning III sample. Of those 21 molecules, 7 had never been confirmed on Mars before. 7 entirely new organic compounds discovered in a single sample. Let that sink in for a moment. 21 different organic molecules, the fundamental building blocks that make life possible, preserved in Martian rock for more than 3 billion years. Protected somehow from the intense radiation that constantly bombards the Martian surface, radiation that should have destroyed these fragile molecules eons ago, yet there they were, intact, waiting to be discovered. Now, organic molecules don't automatically mean life. This is crucial to understand. The term organic simply refers to carbon-based compounds. They can form through biological processes, yes, but also through purely geological mechanisms or arrive on meteorites from space. Scientists cannot yet determine which pathway created the molecules found in Mary Anning III. Both explanations remain possible. However, what this discovery proves beyond doubt is that ancient Mars possessed the right chemistry to support life. The ingredients were there. Carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur, the essential elements that combine to form proteins, nucleic acids, lipids, all the molecular machinery that powers living cells. Mars had these building blocks in abundance. Living on Mars, even billions of years ago when conditions were favorable, would have presented immense challenges. The lower gravity, the thinner atmosphere, the intense radiation from space, the dramatic temperature swings between day and night. If you're interested in understanding just how difficult surviving on Mars would be, check out my other video called Why Your First Year on Mars Would Be the Hardest, where I break down all the physical and psychological challenges humans would face. The link is in the description. The diversity of organic molecules discovered is particularly significant. It's not just one or two compounds, it's an entire suite of different molecules, suggesting complex chemistry was occurring on ancient Mars. On Earth, when we find diverse organic assemblages in rocks, it usually indicates active chemical cycling, often driven by biological processes. Consider the environments where these samples were collected. Jezero Crater and Gale Crater were both ancient lake beds, places where water persisted for potentially millions of years. Sediments accumulated slowly on lake bottoms, layer upon layer, burying organic matter and creating conditions where it could be preserved. Rivers flowing into these lakes brought nutrients from surrounding highlands, creating chemical gradients and energy sources that microbes could exploit. On Earth, similar environments are biological hotspots. Lake sediments teem with bacteria, archaea, and other microorganisms that thrive at the interface between water and sediment. They metabolize minerals, cycling elements through chemical pathways that leave distinctive signatures in the rock record. When geologists examine ancient lake deposits on Earth, they can often identify past biological activity through mineral patterns and organic residues. The question haunting researchers is whether Mars followed the same pattern. Did life emerge in those ancient lakes, metabolizing available chemicals, reproducing, evolving, leaving traces embedded in the rock? Or did geological processes alone create the complex chemistry we're now uncovering? Answering this question requires more than rovers can provide. This is where the Mars Sample Return mission becomes absolutely critical. NASA and the European Space Agency are collaborating on an ambitious plan to bring Martian rocks back to Earth. Perseverance has been collecting and caching samples in sealed titanium tubes, depositing them at specific locations on the Martian surface. Future missions will retrieve these tubes and launch them into Martian orbit, where a spacecraft will capture them and begin the long journey home. Why go through such extraordinary effort and expense? Because the most sophisticated instruments we possess, the ones capable of definitively identifying biosignatures, are simply too large and complex to send to Mars. Mass spectrometers with resolution thousands of times better than what rovers carry. Electron microscopes that can image individual molecules. Isotope analyzers that can distinguish between biological and geological processes with near certainty. These tools exist only in Earth laboratories. Bringing samples back allows hundreds of researchers across dozens of institutions to examine the same rocks using different techniques, cross-checking results, building consensus. It's how we'll move from intriguing possibilities to confirmed discoveries. It's how we'll know for certain whether life once existed on Mars. But there's another mystery that has scientists equally puzzled: methane. This simple molecule, consisting of one carbon atom bonded to 4 hydrogen atoms, has been detected sporadically in the Martian atmosphere by Curiosity's sample analysis at Mars instrument known as SAM. On Earth, roughly 90% of atmospheric methane comes from biological sources: bacteria in wetlands, microbes in termite guts, livestock digestion. Life produces methane. Curiosity has been detecting methane in Gale Crater since 2013, but the behavior of this gas is bizarre. It appears at night and vanishes during daylight. It fluctuates with the Martian seasons. Occasionally, it spikes to levels 40 times higher than background readings, then drops back down. These patterns don't match what we'd expect from a simple geological source steadily releasing gas. Even stranger, the European Space Agency's Trace Gas Orbiter, specifically designed to detect atmospheric methane from orbit, has found essentially nothing. Zero. How can one instrument detect methane on the surface while another finds none in the atmosphere directly above? This contradiction has sparked intense scientific debate. Ashwin Vasavada, Curiosity's project scientist at NASA's Jet Propulsion Laboratory, described it perfectly. It's a story with a lot of plot twists. Some researchers propose that methane is being released from subsurface reservoirs, ancient pockets of gas trapped in rock formations. Others suggest it's being produced by ongoing chemical reactions between water and minerals deep underground, a process called serpentinization that doesn't require life. However, a more recent analysis published in 2025 has questioned whether Curiosity's methane detections are even reliable. Scientists examining the instrument's calibration and potential contamination issues suggested that some of the readings might be instrumental artifacts rather than real Martian methane. This doesn't invalidate all the detections, but it adds uncertainty to an already puzzling situation. Science isn't about absolute certainty, it's about following evidence wherever it leads, even when that evidence is contradictory or confusing. The methane mystery perfectly illustrates this. We have detections that might be real, might be instrumental noise. We have biological explanations, geological explanations, atmospheric chemistry explanations. The truth likely involves multiple processes we haven't fully understood yet. What we do know is that Mars is far more chemically active than previously believed. For decades, scientists thought of Mars as essentially dead, a frozen museum preserving its ancient past but experiencing little ongoing chemistry. That view has been completely overturned. Mars is dynamic, with seasonal changes, mysterious methane fluctuations, perchlorates in the soil that could provide energy for microbes, and subsurface water ice that occasionally melts. Let's zoom out for a moment and consider the bigger picture. Why does this matter? Why should we care whether microbes once lived in Martian lakes billions of years ago? Because this question touches the deepest mysteries of existence. Are we alone in the universe? Is life an inevitable consequence of chemistry when conditions are right? Or is Earth a cosmic fluke, the only place in the vast cosmos where the spark of biology ignited? If life arose independently on Mars, it would suggest that life is common throughout the universe. Think about it. Two planets in the same solar system, both developing life separately. If that happened here, it's probably happened countless times across billions of star systems in our galaxy alone. The universe could be teeming with life, from simple microbes to complex civilizations. Alternatively, if Martian life and Earth life share a common origin that's equally profound. Rocks blasted off Mars by asteroid impacts have landed on Earth throughout geological history. We've found Martian meteorites in Antarctica and other locations. If life originated on one planet and spread to the other through these natural spacecraft, it demonstrates that biology can survive and propagate across interplanetary space. There's even a hypothesis called panspermia, suggesting life might have originated on Mars first, then seeded Earth. In the early solar system, Mars cooled faster than Earth and may have had liquid water and stable conditions earlier. If life emerged there first, Martian microbes hitchhiking on meteorites could have colonized our planet. We might all be descendants of ancient Martians. This isn't science fiction, it's serious scientific hypothesis supported by experimental evidence. Researchers have shown that certain extremophile bacteria can survive the shock of meteorite impacts, the vacuum and radiation of space, and the fiery entry through an atmosphere. Panspermia is controversial but scientifically plausible. Understanding Mars's biological history also informs our search for life elsewhere. Europa, one of Jupiter's moons, has a subsurface ocean beneath its icy shell. Enceladus, orbiting Saturn, has geysers of liquid water erupting into space. Titan has lakes and seas of liquid methane and ethane. These worlds represent potential habitats where life might exist today, not billions of years ago, but right now. The techniques we're developing to search for biosignatures on Mars, the instruments we're designing, the analytical methods we're refining, all of this will be applied to exploring those distant moons. Every discovery on Mars accelerates our ability to answer the ultimate question. Does life exist beyond Earth? Consider the sheer improbability of what we're attempting. Mars is, on average, about 225 million kilometers from Earth. That distance varies considerably depending on where both planets are in their orbits, ranging from about 54 million kilometers at closest approach to over 400 million kilometers when they're on opposite sides of the Sun. Communication signals traveling at the speed of light take between 4 and 24 minutes to cross that gulf, depending on planetary positions. This communication delay means rovers cannot be controlled in real time. Engineers on Earth send commands, then wait. The rover executes instructions autonomously, dealing with obstacles and unexpected situations using its onboard artificial intelligence. Only hours later do mission controllers receive confirmation that operation succeeded or failed. It's like performing surgery while wearing a blindfold with your hands tied, receiving updates about what happened yesterday. Despite these challenges, Curiosity has driven over 31 kilometers across Martian terrain, drilled dozens of rock samples, analyzed thousands of targets, and operated continuously for nearly 14 years. It was designed for a 2-year mission. Perseverance, though younger, is already proving equally resilient, methodically working through its sample collection campaign while testing technologies for future human missions. Both rovers are powered by radioisotope thermoelectric generators, essentially nuclear batteries, that convert heat from decaying plutonium-238 into electricity. These power sources will continue functioning for years, possibly decades, limited eventually by mechanical wear rather than energy depletion. As long as their wheels turn and their instruments function, they'll keep exploring, keep analyzing, keep sending data across the void. The rocks they're studying tell stories spanning billions of years. When you look at a Martian rock in rover images, you're seeing a geological archive. Layers represent different environmental conditions as they were deposited. Minerals indicate what chemicals were dissolved in ancient waters. Textures reveal whether sediments settled gently in still lakes or were tumbled violently by flowing rivers. Reading these stories requires expertise spanning multiple disciplines. Geologists interpret rock structures and formation processes. Chemists analyze mineral compositions and elemental abundances. Biologists evaluate whether observed features could represent biosignatures or have purely abiotic explanations. Atmospheric scientists model ancient climate conditions. Planetary scientists integrate all this information into comprehensive models of Martian history. The Bright Angel Formation that Perseverance is currently studying represents a particularly informative chapter. The rocks there are mudstones, fine-grained sedimentary deposits that formed in quiet water environments. Mudstones are excellent at preserving organic matter because they accumulate slowly, grain by grain, creating anaerobic conditions where bacteria cannot easily decompose buried material. On Earth, some of our most important fossil deposits are found in mudstones and shales. The Burgess Shale in Canada, containing exquisitely preserved fossils from the Cambrian period over 500 million years ago. The Solnhofen limestone in Germany, where Archaeopteryx fossils document the evolution of birds from dinosaurs. These formations preserve not just bones, but soft tissues, delicate structures that normally decay quickly. Could Martian mudstones preserve similar evidence? Possibly. If microbes formed biofilms on ancient lake bottoms, those structures might leave textural signatures visible under microscopes. If colonies of bacteria metabolized minerals, they might create distinctive chemical zonation patterns. If microbial mats trapped and bound sediments, They could produce laminated structures called stromatolites, which are among the oldest evidence for life on Earth. Perseverance carries an instrument specifically designed to search for such features. SHERLOC, which stands for Scanning Habitable Environments with Raman and Luminescence for Organics and Chemicals, uses an ultraviolet laser to analyze rock surfaces at microscopic scales. It can detect organic molecules, map their distribution, and identify associated minerals, all without collecting samples. Working alongside SHERLOC is PIXEL, the planetary instrument for X-ray lithochemistry. This device uses X-ray fluorescence to determine the elemental composition of rocks with extraordinary precision. By mapping how elements like iron, sulfur, phosphorus, and carbon are distributed within rock samples, PIXEL can identify chemical signatures that might indicate biological activity. Together, these instruments provide a 1-2 punch. SHERLOC identifies organic molecules, and PIXEL maps the elemental chemistry surrounding them. When scientists see organic carbon co-located with specific mineral assemblages like iron phosphates and sulfides, especially in nodular or layered structures, it raises the possibility of biological involvement. But interpretation remains challenging. Life isn't the only process that concentrates organic molecules or creates distinctive mineral patterns. Hydrothermal systems, where hot water circulates through rocks, can produce similar features. Meteoritic infall delivers organic compounds to planetary surfaces. Atmospheric chemistry can synthesize simple organic molecules from carbon dioxide and water vapor under ultraviolet radiation. This is why scientists emphasize that current findings are suggestive but not conclusive. They're seeing patterns consistent with biology, but they cannot yet rule out non-biological explanations. It's like finding footprints in the mud. They might indicate an animal passed by, or they might be impressions left by rocks tumbling during a flood. Context matters. Additional evidence is needed. The Mars scientific community has developed strict criteria for claiming detection of life. These criteria, known as biosignature standards, require multiple independent lines of evidence all pointing toward the same conclusion. A single observation, no matter how intriguing, is insufficient. Scientists need patterns, correlations, isotopic signatures, contextual information, and ideally, multiple examples from different locations. This rigorous approach exists because the claim that we've discovered extraterrestrial life is so extraordinary. Carl Sagan famously said extraordinary claims require extraordinary evidence. The scientific community remembers controversial announcements from the past that didn't hold up under scrutiny. In 1996, NASA scientists announced possible fossil microbes in a Martian meteorite found in Antarctica. That claim remains hotly debated and unresolved nearly 30 years later. The meteorite in question, designated ALH 84001, contains carbonate globules with tiny structures that resembled fossilized bacteria under electron microscopes. It also contained organic molecules called polycyclic aromatic hydrocarbons, magnetic mineral crystals similar to those produced by some Earth bacteria, and iron sulfides associated with the organic compounds. Multiple lines of evidence, all seemingly pointing toward ancient Martian life. However, subsequent research showed that all these features could form through non-biological processes. The organic molecules might have been contamination from Antarctic ice. The mineral crystals could have formed through inorganic chemical precipitation. The bacteria-like structures might simply be mineral artifacts too small to have been living cells. While some researchers still believe ALH 84001 contains genuine biosignatures, the scientific consensus remains skeptical. This cautionary tale influences how researchers approach current Mars findings. They're determined not to repeat past mistakes. Every claim is scrutinized, every alternative explanation explored, every possible source of error or contamination investigated. This might seem overly cautious, but it's how science protects itself from false conclusions. Better to be conservative now than make premature announcements that later prove incorrect. Yet despite this caution, the excitement within the scientific community is palpable. The combination of findings from both rovers, the diversity of organic molecules, the specific mineral assemblages, the geological context, everything is pointing in the same direction. Not proof, not yet, but the strongest collection of evidence ever assembled suggesting Mars once supported life. Let's talk about what ancient Martian life might have been like if it existed. We're definitely not talking about complex organisms. No plants, no animals, nothing remotely resembling multicellular life. The time frame we're discussing, 3 to 4 billion years ago, corresponds to the Archean eon on Earth, when life was exclusively microscopic and single-celled. Martian microbes, if they existed, probably resembled Earth's simplest bacteria and archaea. Single cells enclosed in membranes containing genetic material and basic metabolic machinery. They would have been chemotrophs, organisms that derive energy from chemical reactions rather than photosynthesis. The early Martian atmosphere probably lacked sufficient oxygen for aerobic respiration, so these organisms would have relied on alternative energy sources. One possibility is methanogenesis, the metabolic process that produces methane. Certain archaea on Earth generate energy by combining hydrogen gas with carbon dioxide, producing methane as a waste product. This process requires no oxygen and can occur in complete darkness, making it ideal for subsurface or deep-water environments. If Martian life existed, methanogens might have been among the dominant organisms. Another possibility is iron reduction. Many Martian rocks contain oxidized iron, giving the planet its distinctive red color. Bacteria called iron-reducing organisms can use oxidized iron as an electron acceptor, essentially breathing iron oxide the way we breathe oxygen. This metabolism releases energy that microbes can harness for growth and reproduction. The presence of reduced iron minerals like vivianite in bright angel rocks might indicate this process occurred. Sulfur metabolism represents yet another possibility. The detection of iron sulfide minerals suggests sulfur compounds were available in ancient Martian environments. Some Earth microbes reduce sulfate to sulfide, generating energy in the process. Others oxidize sulfide back to sulfate, creating the opposite reaction. These complementary metabolisms can establish complex sulfur cycles in microbial communities, with different species occupying different chemical niches. If Martian life developed these metabolisms, entire ecosystems might have existed in ancient lakes and groundwater systems. Microbes living in sediments, processing minerals, releasing gases, creating chemical gradients that other species exploited. A hidden biosphere, invisible to the naked eye but profoundly influencing the planet's chemistry. This raises a fascinating question. If life existed on ancient Mars, where did it go? Mars today is seemingly sterile, at least on the surface. The thin atmosphere provides almost no protection from ultraviolet radiation, which is lethal to known life forms. The lack of liquid water on the surface makes metabolism impossible. Perchlorates in the soil are highly toxic oxidizers. Surface conditions are utterly hostile to biology, but Mars wasn't always this way. Something catastrophic happened. Approximately 3.5 to 4 billion years ago, Mars lost most of its atmosphere. Without a global magnetic field to shield it from solar wind, charged particles from the Sun gradually stripped away the Martian atmosphere, molecule by molecule, over hundreds of millions of years. As atmospheric pressure dropped, liquid water became unstable. Lakes evaporated or froze. Rivers dried up. The planet transformed from potentially habitable to hostile. Any surface life would have perished during this transition, but subsurface life might have survived. On Earth, we've discovered extensive deep biospheres, ecosystems of microorganisms living kilometers beneath the surface in groundwater, rock fractures, even solid bedrock. These organisms exist in complete isolation from sunlight, deriving energy solely from geological processes. They grow incredibly slowly, reproduce perhaps once per century, but they persist. Could similar deep biospheres exist on Mars today? Quite possibly. Water ice exists beneath the Martian surface, confirmed by radar measurements and exposed in fresh impact craters. At sufficient depth, geothermal heat from Mars's interior could maintain liquid water. Chemical energy from water-rock interactions could sustain metabolism. All the requirements for microbial life might exist underground, beyond the reach of current rovers. This possibility makes the search for present-day Martian life extremely challenging but tantalizing. Surface missions can only scratch the uppermost layers of the planet. To search for extant life, we need to drill deep, perhaps hundreds of meters or more, accessing subsurface aquifers and rock formations where conditions might remain habitable. Such missions are technologically feasible but expensive and complex. Meanwhile, certain locations on Mars might provide windows into the subsurface. Caves and lava tubes could shelter environments protected from surface radiation. Deep canyons like Valles Marineris might expose ancient rock layers and subsurface water. Impact craters excavate material from depth, bringing it to the surface where rovers can analyze it. Each represents a potential shortcut to accessing subsurface environments. The meteorite in question, designated ALH 84001, contains carbonate globules with tiny structures that resembled fossilized bacteria under electron microscopes. It also contained organic molecules called polycyclic aromatic hydrocarbons, magnetic mineral crystals similar to those produced by some Earth bacteria, and iron sulfides associated with the organic compounds. Multiple lines of evidence, all seemingly pointing toward ancient Martian life. However, subsequent research showed that all these features could form through non-biological processes. The organic molecules might have been contamination from Antarctic ice. The mineral crystals could have formed through inorganic chemical precipitation. The bacteria-like structures might simply be mineral artifacts too small to have been living cells. While some researchers still believe ALH 84001 contains genuine biosignatures, the scientific consensus remains skeptical. This cautionary tale influences how researchers approach current Mars findings. They're determined not to repeat past mistakes. Every claim is scrutinized, every alternative explanation explored, every possible source of error or contamination investigated. This might seem overly cautious, but it's how science protects itself from false conclusions. Better to be conservative now than make premature announcements that later prove incorrect. Yet despite this caution, the excitement within the scientific community is palpable. The combination of findings from both rovers, the diversity of organic molecules, the specific mineral assemblages, the geological contexts, everything is pointing in the same direction. Not proof, not yet, but the strongest collection of evidence ever assembled, suggesting Mars once supported life. Let's talk about what ancient Martian life might have been like if it existed. We're definitely not talking about complex organisms. No plants, no animals, nothing remotely resembling multicellular life. The time frame we're discussing, 3 to 4 billion years ago, corresponds to the Archean eon on Earth, when life was exclusively microscopic and single-celled. Martian microbes, if they existed, probably resembled Earth's simplest bacteria and archaea. Single cells enclosed in membranes, containing genetic material and basic metabolic machinery. They would have been chemotrophs, organisms that derive energy from chemical reactions rather than photosynthesis. The early Martian atmosphere probably lacked sufficient oxygen for aerobic respiration, so these organisms would have relied on alternative energy sources. One possibility is methanogenesis, the metabolic process that produces methane. Certain archaea on Earth generate energy by combining hydrogen gas with carbon dioxide, producing methane as a waste product. This process requires no oxygen and can occur in complete darkness, making it ideal for subsurface or deep-water environments. If Martian life existed, methanogens might have been among the dominant organisms. Another possibility is iron reduction. Many Martian rocks contain oxidized iron, giving the planet its distinctive red color. Bacteria called iron-reducing organisms can use oxidized iron as an electron acceptor, essentially breathing iron oxide the way we breathe oxygen. This metabolism releases energy that microbes can harness for growth and reproduction. The presence of reduced iron minerals like vivianite in bright angel rocks might indicate this process occurred. Sulfur metabolism represents yet another possibility. The detection of iron sulfide minerals suggests sulfur compounds were available in ancient Martian environments. Some Earth microbes reduce sulfate to sulfide, generating energy in the process. Others oxidize sulfide back to sulfate, creating the opposite reaction. These complementary metabolisms can establish complex sulfur cycles in microbial communities, with different species occupying different chemical niches. If Martian life developed these metabolisms, entire ecosystems might have existed in ancient lakes and groundwater systems. Microbes living in sediments, processing minerals, releasing gases, creating chemical gradients that other species exploited. A hidden biosphere, invisible to the naked eye but profoundly influencing the planet's chemistry. This raises a fascinating question. If life existed on ancient Mars, where did it go? Mars today is seemingly sterile, at least on the surface. The thin atmosphere provides almost no protection from ultraviolet radiation, which is lethal to known life forms. The lack of liquid water on the surface makes metabolism impossible. Perchlorates in the soil are highly toxic oxidizers. Surface conditions are utterly hostile to biology, but Mars wasn't always this way. Something catastrophic happened. Approximately 3.5 to 4 billion years ago, Mars lost most of its atmosphere. Without a global magnetic field to shield it from solar wind, charged particles from the Sun gradually stripped away the Martian atmosphere, molecule by molecule, over hundreds of millions of years. As atmospheric pressure dropped, liquid water became unstable. Lakes evaporated or froze. Rivers dried up. The planet transformed from potentially habitable to hostile. Any surface life would have perished during this transition, but subsurface life might have survived. On Earth, we've discovered extensive deep biospheres, ecosystems of microorganisms living kilometers beneath the surface in groundwater, rock fractures, even solid bedrock. These organisms exist in complete isolation from sunlight, deriving energy solely from geological processes. They grow incredibly slowly, reproduce perhaps once per century, but they persist. Could similar deep biospheres exist on Mars today? Quite possibly. Water ice exists beneath the Martian surface, confirmed by radar measurements and exposed in fresh impact craters. At sufficient depth, geothermal heat from Mars's interior could maintain liquid water. Chemical energy from water-rock interactions could sustain metabolism. All the requirements for microbial life might exist underground, beyond the reach of current rovers. This possibility makes the search for present-day Martian life extremely challenging but tantalizing. Surface missions can only scratch the uppermost layers of the planet. To search for extant life, we need to drill deep, perhaps hundreds of meters or more, accessing subsurface aquifers and rock formations where conditions might remain habitable. Such missions are technologically feasible but expensive and complex. Meanwhile, certain locations on Mars might provide windows into the subsurface. Caves and lava tubes could shelter environments protected from surface radiation. Deep canyons like Valles Marineris might expose ancient rock layers and subsurface water. impact craters excavate material from depth, bringing it to the surface where rovers can analyze it. Each represents a potential shortcut to accessing subsurface environments. Future missions might specifically target these locations. Imagine a rover equipped with climbing capabilities exploring canyon walls, or a drone that could descend into cave systems, or a drill rig capable of penetrating hundreds of meters into the Martian crust. These technologies are under development, representing the next generation of Mars exploration beyond what Perseverance and Curiosity can accomplish. Europe's ExoMars. Rosalind Franklin rover, currently scheduled for launch in the late 2020s, will carry a drill capable of reaching 2 meters below the surface. That might not sound impressive compared to terrestrial drilling operations that routinely penetrate kilometers, but on Mars it's revolutionary. Those 2 meters could access material completely untouched by surface radiation, preserving organic molecules and potential biosignatures that would be destroyed in the uppermost layers. The scientific return from even shallow subsurface drilling could be extraordinary. On Earth, subsurface environments harbor microbial communities dramatically different from surface ecosystems. They're dominated by slow-growing extremophiles adapted to darkness, low nutrients, and stable temperatures. If Mars hosts similar communities, accessing them would transform our understanding of the planet's biology. There's also the intriguing possibility of seasonal habitable environments. Recent discoveries show that liquid water might exist temporarily on Mars under specific conditions. Recurring slope lineae, dark streaks that appear on Martian slopes during warm seasons, might represent briny water flowing briefly before evaporating or freezing. The salts dissolved in this water dramatically lower its freezing point, allowing it to remain liquid at temperatures where pure water would solidify. Perchlorates, those toxic compounds found in Martian soil, have this property. They're hygroscopic, meaning they absorb water from the atmosphere, and they depress freezing points. Concentrated perchlorate brines can remain liquid down to -70 degrees Celsius. While such brines would be extremely challenging environments for life, some Earth microbes tolerate similarly harsh conditions. Certain halophiles, salt-loving microorganisms, thrive in saturated brines on Earth. They've evolved specialized proteins and cellular mechanisms to cope with extreme salinity and low water activity. If similar adaptations evolved on Mars, microbial life might persist in transient brines, going dormant during dry periods and becoming active when liquid water appears. Testing this hypothesis requires landing missions in locations where brines might form, equipped with instruments capable of detecting low levels of metabolic activity. This is challenging because we can't risk contaminating potentially habitable environments with Earth microbes hitchhiking on spacecraft. Planetary protection protocols strictly regulate where missions can land and what level of sterilization is required. Balancing exploration with protection is one of the great challenges in astrobiology. We want to search everywhere for life, but we also have ethical and scientific obligations not to contaminate pristine environments. If we inadvertently introduce Earth microbes to Mars and they survive, we might confuse our own contamination with indigenous Martian life. Worse, Earth organisms might outcompete or harm native Martian ecosystems if they exist. This brings us to an important philosophical question. What responsibilities do we have toward potential Martian life? If we discover extant microbes, do they have intrinsic value, deserving protection? Should Mars be preserved as a wilderness, off-limits to human exploitation? Or do human interests take precedence, allowing us to terraform and colonize the planet regardless of indigenous biology? These questions lack easy answers. They involve values, ethics, and priorities that extend beyond pure science. Different people and cultures might reach different conclusions based on their worldviews and philosophical commitments. What seems clear is that discovering life on Mars, whether fossil or living, would force humanity to grapple with these issues in ways we've never had to before. The late planetary scientist Carl Sagan wrote extensively about our obligations to other worlds. He argued that the discovery of even microbial life elsewhere would represent a milestone of cosmic significance, deserving the utmost care and respect. Other thinkers emphasize human needs and argue that an uninhabited Mars could and should be transformed to support Earth's growing population and preserve our species against existential risks. Perhaps the answer depends on what we find. If Mars is truly dead with no extant life and only fossil remnants, the ethical calculus might favor human utilization. If living ecosystems exist, the argument for protection strengthens considerably. If Martian life shares a common origin with Earth life, they're essentially distant relatives, which might influence our moral obligations differently than if they represent an entirely independent genesis. These are conversations humanity needs to have sooner rather than later. SpaceX is developing Starship with the explicit goal of establishing permanent human settlements on Mars within the next couple of decades. NASA's Artemis program aims to establish lunar infrastructure as a stepping stone to Mars missions in the 2030s. China has announced ambitious plans for Mars sample return and eventual crewed missions. The era of human Mars exploration is approaching rapidly. Before boots touch Martian soil, we need international agreements about planetary protection, resource utilization, territorial claims, and conservation. The Outer Space Treaty of 1967 provides a framework stating that celestial bodies cannot be claimed by nations and should be explored for the benefit of all humanity. But it predates our current understanding of Mars and doesn't address many contemporary concerns. Let's return to the science for a moment and consider the implications if life never existed on Mars despite favorable conditions. That would be equally profound in its own way. It would suggest that the transition from chemistry to biology is extraordinarily difficult, perhaps requiring specific circumstances that Mars lacked, despite having water, organic molecules, and energy sources. On Earth, life appears to have emerged relatively quickly in geological terms. The oldest confirmed fossils are approximately 3.5 billion years old, and some disputed evidence suggests life might have existed 3.8 or even 4 billion years ago. Earth formed 4.54 billion years ago, meaning life appeared within the first billion years or so, possibly much sooner. This rapid emergence suggests that given the right conditions, biogenesis might be almost inevitable. However, we have a sample size of exactly 1. Earth is the only planet where we know life exists. Drawing conclusions from a single data point is scientifically problematic. Mars provides our first opportunity to test whether life emerges wherever conditions permit, or whether Earth represents a unique cosmic accident. If Mars proves lifeless despite having ancient lakes, organic chemistry, and energy sources, it would suggest additional requirements we haven't identified. Perhaps a planet needs plate tectonics to continuously recycle nutrients and maintain chemical disequilibrium. Perhaps a magnetic field is essential to protect prebiotic chemistry from radiation long enough for life to emerge. Perhaps the specific timing of water availability matters critically, or the concentration of particular elements, or factors we haven't even considered. Alternatively, Mars might have been on the cusp of developing life but ran out of time. If the atmospheric collapse happened earlier than we think, perhaps only a few 100 million years after liquid water appeared, that might have been insufficient for biogenesis despite favorable conditions. Life might require not just the right chemistry, but also stability over timescales we haven't properly appreciated. This uncertainty underscores why sample return is so vital. Laboratory analyses could definitively determine whether organic molecules in Martian rocks have biological or abiotic origins by examining their isotopic compositions and molecular structures, with precision impossible on Mars. They could identify preserved cellular structures under electron microscopes. They could search for homochirality, the tendency of biological molecules to favor specific mirror image forms. On Earth, life uses exclusively left-handed amino acids and right-handed sugars. This homochirality is a strong biosignature because abiotic chemistry produces equal mixtures of left and right-handed molecules. If Martian organics show similar handedness preferences, it would strongly suggest biological origins. If they're racemic mixtures with no preference, it would support abiotic formation. The planned sample return architecture is extraordinarily complex. After Perseverance finishes collecting samples, currently expected around 2028, 2 small rocket-equipped fetch rovers will land near the cached sample tubes. These rovers, about the size of small cars, will collect the tubes and transport them to a Mars ascent vehicle, essentially a small rocket sitting on a landing platform. The Mars ascent vehicle will launch the samples into Martian orbit inside a basketball-sized container, the first rocket launch from another planet in human history. An Earth return orbiter provided by the European Space Agency will rendezvous with this container, capture it, and seal it inside a biocontainment system to prevent any possibility of contaminating Earth with Martian material. The return journey will take approximately 2 years, culminating in a high-speed entry into Earth's atmosphere. The sample container will separate from the orbiter and descend to a landing site in the Utah desert, where it will be recovered and transported to a specially constructed biosafety containment facility. There, samples will undergo rigorous analysis while remaining isolated from Earth's environment until proven safe. This entire mission architecture spans roughly 15 years from Perseverance's landing in 2021 to samples arriving on Earth potentially in the mid to late 2030s. It involves multiple spacecraft, international collaboration, technologies never before attempted, and costs estimated at $7 to $9 billion. It represents one of the most ambitious robotic missions ever conceived. Yet despite the expense and complexity, scientists consider it essential. Some questions simply cannot be answered remotely. The instruments needed to definitively identify biosignatures, to distinguish unambiguously between biological and geological processes, to extract and sequence potential genetic material, these technologies are too large, too power-hungry, and too delicate to operate on Mars with current capabilities. Moreover, bringing samples to Earth allows analyses using techniques not yet invented. When the Apollo missions returned lunar samples in the late 1960s and early 70s, scientists analyzed them with the best technology available at the time. Decades later, researchers are still studying those same samples using instruments and methods that didn't exist during Apollo. Each new technology reveals additional information locked in the rocks. Martian samples will similarly provide research opportunities for generations. The initial analyses will address immediate questions about biosignatures and ancient habitability. Future studies might extract information about Martian climate history, atmospheric evolution, magnetic field dynamics, impact chronology, and countless topics we haven't anticipated. These samples will become reference materials, analogous to how lunar samples remain invaluable research subjects more than 50 years after collection. There's also profound symbolic value in holding Martian rocks on Earth, pieces of another world delivered across the interplanetary void. When scientists first examine samples under microscopes in terrestrial laboratories, when they measure isotopes with mass spectrometers, when they search for fossilized microbes with electron imaging, they'll be doing something unprecedented in human history, analyzing extraterrestrial material collected specifically to search for signs of life beyond Earth. The implications extend beyond Mars. Success with Mars sample return establishes capabilities applicable to other targets. Europa sample return missions become conceivable, though far more challenging given Jupiter's distance and radiation environment. Enceladus plume sample return, collecting material ejected from the Moon's subsurface ocean, represents another possibility. Asteroid and comet sample return missions expand our understanding of solar system formation and organic chemistry delivery to early planets. Japan's Hayabusa missions have already returned samples from asteroids Itokawa and Ryugu. NASA's OSIRIS-REx returned samples from asteroid Bennu in 2023. These missions demonstrated that sample return technology works and provides scientific value far exceeding remote observation. The same principles apply to Mars, but scaled up enormously given the planet's size, gravity, and distance. Meanwhile, both Curiosity and Perseverance continue their investigations, daily adding to our knowledge. Every rock they analyze, every image they capture, every measurement they record contributes to our evolving understanding of Mars. These rovers have fundamentally transformed how we perceive the red planet, from a cold, dead world to a dynamic, chemically active planet with a complex and possibly biological past. The images they send back have aesthetic power beyond their scientific value, panoramas showing layered cliff faces with strata representing millions of years of geological history, close-ups revealing intricate mineral veins cutting through ancient rocks, self-portraits showing the rovers against dramatic Martian landscapes. These images inspire wonder, reminding us that robotic explorers are extending human presence across the solar system. Consider the engineering achievement these missions represent. Designing machinery that survives the violent shock of landing, the temperature extremes of Martian nights dropping below -100 Celsius and days warming to near freezing, the abrasive dust that infiltrates mechanisms, the radiation bombardment that degrades electronics. Curiosity and Perseverance incorporate thousands of innovations, from the Sky Crane landing system to radiation-hardened computers to autonomous navigation algorithms. The wheels on both rovers tell a story of Martian harshness. Curiosity's aluminum wheels have suffered significant damage from sharp rocks, developing holes and tears that concerned engineers early in the mission. They modified driving strategies, choosing routes more carefully and developing algorithms that avoid particularly hazardous terrain. Perseverance incorporated these lessons, using slightly thicker aluminum and modified tread patterns that distribute stress more effectively. Even seemingly simple tasks become enormously complex on Mars. Drilling into rock requires carefully calibrated force. Too little, and the drill bit skitters across the surface without penetrating. Too much, and you risk breaking the bit or jamming the mechanism, potentially mission-ending failures when repair is impossible. The rover must position itself precisely, extend the robotic arm, apply appropriate pressure, monitor vibrations and motor currents, adjust in real time, then carefully extract the bit without contaminating the sample. This entire process happens autonomously, with commands uploaded hours earlier from Earth. If something goes wrong, the rover must recognize the problem and stop safely without human intervention. Then mission controllers receive telemetry indicating what failed, spend days analyzing the situation, develop modified commands, upload new instructions, and try again. Operations that would take minutes with direct human control consume weeks or months through remote robotic execution. Despite these challenges, both rovers have achieved remarkable success. Curiosity has collected and analyzed dozens of drilled samples, creating a detailed geochemical profile of Jezero Crater's history. Perseverance has collected 27 samples as of its latest update, carefully selected to represent diverse geological environments and maximize scientific return when they eventually reach Earth. Each sample tells part of Mars's story. Some contain volcanic minerals indicating when magma erupted and solidified, providing age constraints through radiometric dating. Others preserve sedimentary structures, showing how water deposited particles, and potentially concentrated organic matter. Still others contain salts and clays documenting chemical interactions between water and rock that created environments potentially suitable for life. The diversity of samples is strategic. If only one or two types of rocks were collected, our understanding would remain limited. By gathering samples representing igneous processes, aqueous alteration, sedimentary deposition, and surface weathering, scientists can reconstruct a comprehensive history. It's like collecting chapters from different parts of a book, allowing you to understand the complete narrative even without reading every page. This sampling strategy reflects decades of Mars exploration experience. Early missions like Viking in the 1970s searched for life directly using biological experiments. Those results were ambiguous and controversial, teaching scientists that simple yes or no tests are insufficient. We needed to understand Martian environments first, determine where and when conditions might have been habitable, then search for biosignatures in those specific contexts. Subsequent missions focused on geological characterization. Mars Global Surveyor mapped the planet's topography and magnetic field remnants. Mars Odyssey and Mars Reconnaissance Orbiter conducted mineralogical surveys identifying clay deposits, sulfates, and other minerals indicating past water. The Spirit and Opportunity rovers investigated specific sites, discovering hematite concretions nicknamed blueberries and sulfate-rich soils indicating ancient acidic waters. Each mission built on previous discoveries, progressively refining our understanding. This systematic approach has now reached the point where we can confidently identify ancient lakebeds, river deltas, and hydrothermal systems, then send rovers to those locations to search for biosignatures. Perseverance's landing site in Jezero Crater was chosen because three different types of evidence converged there. First, orbital imagery revealed a dramatic fan-shaped formation at the crater's western edge, interpreted as an ancient river delta, where a river once flowed into a lake filling the crater. Deltas on Earth are excellent environments for preserving organic matter and potential fossils because fine sediments bury biological material rapidly, protecting it from oxidation and decay. Second, spectroscopic measurements from orbit detected clay minerals within the delta. These clays, called phyllosilicates, form through prolonged interaction between water and rock under neutral to slightly alkaline pH conditions, exactly the chemistry considered most favorable for life. Their presence confirmed that not only did water exist, but it persisted long enough to chemically alter rocks. Third, the crater contains diverse geological units including volcanic rocks, sedimentary deposits, and what appear to be carbonate deposits along the shoreline, where the ancient lake reached its maximum extent. This diversity means Perseverance can study multiple environments within a relatively small area, maximizing scientific return during its operational lifetime. The mission has exceeded expectations. Not only has Perseverance collected excellent samples, but its companion helicopter, Ingenuity, has revolutionized Mars exploration. Initially planned for just 5 test flights to demonstrate powered flight in Mars's thin atmosphere, Ingenuity has completed over 70 flights, scouting terrain ahead of the rover and demonstrating capabilities for future missions. Ingenuity proved that aerial exploration on Mars is viable. Future missions might deploy larger helicopters or drones capable of carrying scientific instruments, covering distances in minutes that take rovers weeks, and accessing terrain impossible for wheeled vehicles. Imagine helicopters surveying canyon walls, investigating caves, or collecting atmospheric samples at various altitudes. The possibilities are transformative. Meanwhile, Curiosity continues exploring Gale Crater's central mountain, Mount Sharp. The rover has been climbing this 5-kilometer-high mound for years, with each elevation gain representing a journey forward in time through Martian history. The lowest layers are oldest, deposited when water filled Gale Crater billions of years ago. Higher layers record the gradual drying and chemical changes as Mars lost its atmosphere and surface water. Mount Sharp preserves a unique record of this transition, arguably the most important environmental shift in Martian history. Understanding exactly when and how Mars transformed from a potentially habitable world to its current state constrains theories about atmospheric loss, climate evolution, and the survival prospects for any life that might have existed. Did the change happen suddenly, perhaps triggered by a massive asteroid impact, or was it gradual, taking hundreds of millions of years as solar wind slowly stripped away the atmosphere? Evidence suggests a complex picture. Atmospheric loss began early, within the first few 100 million years of Martian history, but continued over billions of years. Some liquid water persisted on the surface perhaps as recently as 2 to 3 billion years ago, after which only episodic flooding occurred from subsurface aquifer breaches. The last surface water might have existed less than a billion years ago in certain locations. This extended timeline creates interesting possibilities for biological evolution if life ever emerged. On Earth, single-celled microbes dominated for roughly 3 billion years before multicellular organisms appeared. If Martian life followed similar timescales and emerged early during the warm, wet period, it might have had a billion years or more to evolve and diversify before surface conditions deteriorated. Could Martian life have achieved complexity beyond simple bacteria? Perhaps not multicellular organisms, which require stable environments and sufficient nutrients to support coordinated cellular structures, but possibly greater diversity than we might initially assume. Earth's microbial world includes extraordinary variety, from methanogens to sulfur oxidizers to photosynthetic cyanobacteria, each adapted to different niches. If Martian ecosystems existed for comparable durations, they might have developed similar ecological complexity, with different microbial species occupying distinct chemical niches, perhaps even forming microbial mats and biofilms analogous to Earth's stromatolites. These layered structures, built by microbial communities trapping and binding sediments, represent some of Earth's oldest fossils and might be preserved in Martian rocks. Perseverance carries instruments specifically designed to identify such structures. Pixel, the planetary instrument for X-ray lithochemistry, can map elemental compositions at microscopic scales, revealing chemical patterns that biological processes create. Sherlock uses ultraviolet lasers to detect organic molecules and map their distribution across rock surfaces, showing whether organics cluster in patterns suggesting biological origin. These capabilities represent a quantum leap beyond previous missions. Earlier rovers could detect organic molecules in bulk samples, but couldn't determine their precise locations or relationships to mineral structures. Now, Perseverance can examine a rock surface millimeter by millimeter, creating detailed chemical maps showing exactly where organics concentrate and how they relate to surrounding minerals. This spatial resolution is crucial because biological processes create distinctive patterns. Microbes don't randomly scatter organic molecules, they concentrate them in cells, excrete them in specific locations, and create chemical gradients in surrounding environments. Finding organics clustered in circular structures resembling cell walls, or concentrated in layers suggesting microbial mats, or associated with specific minerals that microbes preferentially colonize, would strengthen biosignature claims enormously. However, geology can also create patterns. Mineral precipitation, fluid flow through fractures, and chemical sorting during sedimentation all produce organized structures that superficially resemble biological features. This is why multiple lines of evidence are essential. No single observation definitively proves biology. Rather, scientists look for convergence, where multiple independent indicators all point toward the same conclusion. The challenge of distinguishing biological from geological processes has occupied scientists studying Earth's oldest rocks for decades. Claimed microfossils from 3.5 billion-year-old Australian rocks have generated controversy because the structures could be mineral artifacts. Chemical signatures interpreted as evidence for life might result from non-biological processes. Even stromatolites, long considered unambiguous biosignatures, can form through purely physical sediment trapping without microbial involvement. These debates inform Mars research. Scientists are acutely aware that extraordinary claims require extraordinary evidence. Any biosignature claim for Mars will face intense scrutiny and demands for rigorous proof that alternative explanations have been eliminated. This is appropriate and necessary, but it also means definitive answers will require time and painstaking analysis. The sample return timeline reflects this reality. Even after samples arrive on Earth, probably not before the mid-2030s, initial analyses will take years. Multiple research teams will examine samples independently, using different techniques and approaches. Results will undergo peer review, alternative explanations will be debated, and consensus will emerge gradually through the normal scientific process. This contrasts with popular expectations of sudden, dramatic discoveries. Media coverage often presents science as producing clear-cut breakthroughs, but reality is messier. Knowledge accumulates incrementally through careful observation, repeated testing, and gradual refinement of hypotheses. The search for life on Mars exemplifies this process, with each mission adding pieces to a puzzle that may take decades to complete. Yet the journey itself has value beyond the destination. Mars exploration has driven technological innovation, inspired new generations of scientists and engineers, and expanded humanity's perspective beyond Earth. The rovers have become cultural icons, with millions following their missions and celebrating their achievements. They represent human curiosity and determination, our drive to explore and understand. There's something profound about machines we built, launched across interplanetary space, and landed on another world, continuing to function years beyond their design lifetimes. Opportunity operated for nearly 15 years before a global dust storm ended its mission in 2018. Curiosity has been exploring for over 12 years and continues strong. These rovers embody human ingenuity and persistence. They also remind us of our cosmic context. Mars is our neighbor, the most Earth-like planet in the solar system, yet it's utterly alien. No breathable air, no liquid water on the surface, temperatures that would kill unprotected humans in minutes. Standing on Mars would feel like standing in Antarctica at midnight during winter, except worse, because the atmosphere provides almost no insulation or pressure. Yet billions of years ago, Mars might have been welcoming. Rivers might have flowed through valleys where rovers now drive. Lakes might have lapped against shorelines now marked only by mineral deposits. Rain might have fallen from cloudy skies onto a landscape that looked surprisingly Earth-like. If you could have stood on ancient Mars 3.5 billion years ago, would you have found a living world? That question drives everything. It motivates the missions, justifies the expense, sustains the research programs. Because if life existed on ancient Mars, if two planets in the same solar system both developed biology, it would transform our understanding of life's prevalence in the universe. It would suggest that wherever conditions permit, given sufficient time, life emerges, and in a galaxy containing hundreds of billions of stars with trillions of planets, that would mean life is common. Conversely, if Mars proves lifeless despite having oceans, organic chemistry, and energy sources, it would suggest life is far rarer than we hope. It would mean something special happened on Earth, some critical factor or fortunate circumstance that Mars lacked. In a strange way, that would make Earth and its biosphere even more precious, a fragile oasis of biology in a predominantly sterile cosmos? Either answer has profound implications. Common life means the universe teems with biology, perhaps intelligence, civilizations we might someday contact. Rare life means we might be alone or nearly so, bearing responsibility as possibly the only conscious observers in vast reaches of space and time. Both scenarios inspire awe and demand that we treat the question with appropriate seriousness. This is why scientists are so careful, so methodical, so insistent on rigorous proof before making claims. They understand what's at stake. The discovery of extraterrestrial life, even fossil microbes, would rank among the most significant scientific achievements in history, comparable to understanding that Earth orbits the Sun, that evolution shaped life's diversity, or that the universe began in a Big Bang. Such momentous discoveries require unimpeachable evidence. They must withstand skeptical scrutiny from scientists worldwide and remain valid as knowledge advances. This standard is appropriate given the implications. Better to spend decades gathering definitive proof than make premature announcements that later crumble under examination. The evidence from Jezero Crater and Gale Crater represents the most compelling findings yet, not proof, but strong indicators that make scientists optimistic. The organic molecules, the specific mineral assemblages, the geological contexts, all align with what we'd expect if microbial life once existed in these ancient lake environments. But consistent with is not the same as proof of. That's the crucial distinction. Many geological processes produce outcomes similar to biological ones. Distinguishing between them requires the kind of detailed laboratory analysis that only sample return enables. Until those samples arrive on Earth and undergo comprehensive study, the question remains tantalizingly open. In the meantime, missions continue. NASA's Mars Sample Return Campaign progresses through its development phases. The European Space Agency's ExoMars rover awaits its launch opportunity, carrying a drill that will probe deeper than any previous mission. China's Tianwen program has successfully placed an orbiter and rover on Mars, with plans for sample return in the early 2030s. India's Mars orbiter mission demonstrated that nations' interplanetary capabilities, with more ambitious missions planned. This international engagement reflects Mars's importance to humanity, not just individual nations. The question of life beyond Earth transcends borders and politics. It speaks to fundamental aspects of human existence, our origins, our place in the cosmos, whether we're alone. These are questions that belong to all humanity, regardless of nationality, culture, or belief system. The exploration of Mars also serves as a proving ground for technologies and strategies needed for human missions. Understanding the planet's resources, hazards, and environments informs planning for eventual crewed expeditions. Learning to operate complex systems remotely, with communication delays and without possibility of immediate assistance, develops capabilities applicable throughout the solar system. Some argue that searching for ancient life is less important than preparing for human colonization, that we should focus on making Mars habitable rather than studying what it once was. This represents a false dichotomy. Both pursuits inform each other. Understanding Martian geology helps identify resources for future settlers. Knowing whether life exists or existed guides planetary protection policies that affect where and how humans can establish bases. Moreover, if we discover that Mars once harbored life but lost it as the planet changed, that story has direct relevance to Earth's future. It reminds us that planetary habitability is not permanent, that atmospheres can be lost, that climates can shift dramatically. Mars serves as a natural experiment in planetary evolution, offering lessons about how worlds live and die. The dried lake beds explored by Curiosity and Perseverance are monuments to what Mars lost. They're also archives preserving evidence of a more hopeful past. Whether those archives contain fossils of Martian life remains to be seen, but the possibility is real enough to justify our continued investigation. As we stand in 2026, the story is far from complete. The most exciting chapters may still lie ahead, preserved in cached sample tubes waiting for retrieval, or in rock formations not yet explored, or in subsurface environments that future missions will access. Each new discovery brings us closer to answering one of humanity's oldest questions. Are we alone? The rovers continue their work, driving across ancient lake beds, analyzing rocks, searching for clues. They represent humanity's extended eyes and hands, exploring on our behalf, sending back images and data that inform and inspire. They're still out there right now, on another world, doing science under alien skies. And perhaps, just perhaps, they're finding evidence that once, long ago, Mars was not a dead world, but a living one. That would change everything. Curious about Mars's future? While scientists search for ancient life, the dream of human colonization faces terrifying realities most people never consider. Watch the video on the screen to discover why living on the red planet might be humanity's most dangerous endeavor yet, far beyond what science fiction prepares us for. See you there.